Hey guys, and welcome to Clay and Campbell's Additional Mathematics series. Presenting episode 1, topic Algebra Part 1. The things we should cover in this episode: real number system, addition and subtraction of polynomials. So, first thing is, what is the number system or the real number system? In mathematics, a real number is a value that represents a quantity along a line. So all values that lies on a number line is of the real number system. So in consideration of the number line, we have learned this in primary school or in basic school for some, where we see a line that we mark out and represent several different values. Generally, we use it with counting numbers, where we have 1, 0, we start at 0, then 1, then 2, then 3, then 4, and so on. So real numbers are all values that lies on the number line is considered of the real number system. So whether it's irrational, rational, whole, integer, it is all in the real number system. So here's an example of a number line. As you can see over this side, things get more negative to infinity, and over this side things get positive, more positive or larger in value to infinity. Lesser in value, more negative, greater in value, more positive to infinity. So real numbers can be thought of as points on infinite. So real numbers can be thought of as points on an infinite. Real numbers can be thought of as points on an infinitely long number line. And the symbol of real number is represented by this fellow here. So the real number system continuing. So systems that fall under the real number systems are natural numbers, whole numbers, integers, rational numbers, irrational numbers. So the first thing we learn is natural numbers. So a natural number is a number that occurs commonly and obviously in nature. As such, it is a whole, non-negative number. The set of natural numbers denote n can be defined in either two ways. N is equal to 0, 1, 2, 3, or n is equal to 1, 2, 3, 4. And there are also definitions of natural numbers, that is, a system that consists of both whole numbers here and counting numbers. Because if we remember well, counting numbers generally starts at 1, so it excludes 0, while in the whole number system, it consists of 0, 1, 2, 3 whole numbers that is whole. And here is a symbol of natural numbers. Next, we're at whole numbers. So whole numbers are simply numbers 0, 1, 2, 3, 4, 5, and so on. So whole numbers, as I said before, is this. So there is no fractional or decimal part and no negatives. That is the key in knowing if this system is a whole number system. So example 5, 49, 980 are all whole numbers. And here is an example of whole numbers on a number line. It emphasizes on no fractions. Next, we're at integers. So an integer, pronounced as integer, is a whole number, not a fractional number, that can be positive, negative, or 0. So examples of integers are -5, 1, 5, 8, 97, and 3, 0, 43. Examples of numbers that are not integers are 1.43, 13 out of 4, 3.14, 0.09, and 5, which should be 5.1, or and 641.1. So the set of integers can be denoted by z, is formally defined as follows: -3, -2, -1, 0, 1, 2, 3 eclipses, and the symbol of integers are represented by this, which is z. So now we're at rational numbers. So in mathematics, a rational number is any number that can be expressed as a quotient or fraction p over q of two integers. So p and q is any number that can be represented as a fraction and has a exact value in its decimal. Don't be confused, because 3 over 19 is a fraction, but it is not rational. It is irrational, because there is no exact representation, or there is no exact value of representing this fraction as a decimal. So rational numbers, we know the difference between it now. Rational numbers are values that represent fractional or decimal parts, but can be represented as exact values in both the fractional form and decimal form, while irrational numbers, on the other hand, are also representing fractional parts and decimal form, but it has no exact value between the fraction form and decimal form. So a real number that is not rational is called irrational. So example, 1.5 is a rational number because 1.5 is equal to 3 over 2. It can be written as a fraction. And here is the example down below. So a rational number is a number that can be represented in the form p over q, where p and q are integers and q is not equal to 0. So now irrational numbers, which are real numbers that cannot be written as simple fractions. So example, a famous example, pi, is an irrational number that has many places of decimal continuously, and this is only an estimate of the place of pi, and you cannot simply write this down as a fraction. We have a popular approximation of 22. We have a popular approximation of 22 out of 7, which is 3.xyz, but is not accurate. So that's why it's irrational. It doesn't have an exact value in its fractional form, and decimal places are generally continuously on and on and on. Not all cases. So another example of an irrational number is root 2. Root 2, that is not an exact value of its decimal form, therefore it's considered an irrational number, similarly to pi. So we're at addition and subtraction of polynomials. So this is the coefficient, this would be the base, and this would be power, the index or the exponent of the expressions we're going to learn. So a to the xn is an algebraic expression where a is the coefficient of x to the n, x is the base, and n is the power index. So like algebraic terms are defined as those algebraic terms which are represented by the same base and power. Example, 2x cubed, 2x to the cube, minus 4x to the cube, total 5x cubed, and negative 7 out of 8x cubed. First example, ax plus 5x plus 12x. So since they are of similar terms, which is similar base, so this on a whole would be x to the 1, but we exclude it because anything to the power of 1 is itself. So these are of the same base and same power, so we can group them by using the distributive law. So we have 8 plus 5 plus 12, and we will get 25x. Next example, 17x squared minus 9x squared. Again, this is of the same base and same exponent, so we can simply group these. So do subtraction of the coefficients and add this, stick it to the answer. So 17 minus 9 x squared, and we would get 8x squared. Next, 9x cubed plus 5x cubed minus 4x cubed. All of these again are of the same base and same exponent, so we can group them and add 9 to 5 and subtract 4 from 9 plus 5. So we put that all in brackets, and using the Bumdas rule, we add before subtracting, and we would get 10x squared. In any ways, if we did subtract these two first and add it, we would have get the same answer in this case. But it's always good to apply the Bumdas rule when doing multiple operations. Example 4. Now this is, these are terms of, there are 3 different groups or like terms in this expression. So when we're doing these now, we have to slow down, and what my teacher would say is we group them by saying, okay, this is x squared, so find the next one which is of x squared, mark it and put them together. Then now this is 7x, so this is of x. Find the next x which is here, mark it out. Then finally 8x cubed, find the next one with x cubed in it, and then that's what I do, mark it out and group them together. So after grouping them, we can apply the same rule that we did up here in the previous examples, and we group the coefficients now. So now this would be 7x plus 3x, so operating on the coefficients, that would be minus 7 plus 3x plus 4 plus 2 x squared plus 8 minus 5 x cubed, until we get our final answer, which is minus 4x plus 6x squared plus 3x cubed. So guys, this is the end of the video. Please like the video if you enjoyed it and share it with your friends who really need this video. And don't forget to click that subscribe button for more videos like this. Bye.